And what chapter was this from?
Chapter 4.
Chapter 4. Okay. All right. So something is an altitude if it meets at if it meets at a 90-degree angle. So if we can prove that, let me just snip the picture in again. If we can prove that this is a 90-degree angle or this is a 90-degree angle, we have enough to prove that it's an altitude because it comes from the vertex B.
Right.
Now I'm a little, you can't tell, I'm a little stuck here because I'm like, oh, I just like wonder how we're going to do this. I guess I better go look back at chapter 4 for like what the requirement is for a right triangle. Because I guess I'm not sure, and just at first glance. Now, do you have any ideas or anything come to mind for you on this one?
Is it with side angle side?
Well, one of the problems I'm seeing, and that's why I was surprised that it was DB here, is that I thought, oh, we'll just prove the triangles are congruent or something like that. But it's that these two angles are the same. I'm sorry, these two sides are the same. So that means it's an isosceles triangle.
Right.
So, okay. And actually I do see how, I guess I do see a path here. Okay. So, the fact that these two angles are the same and they fall on a line tells you that the two angles have to add up to 180 degrees. The measure of angle ADB plus the measure of angle BDC has to add up to 180. That's the definition of supplementary angles or a linear pair. Since they're congruent, we can find that the measure of one of the angles is 90, and since it's the same as the other angle, it's 90 as well. Then we can prove that it is a right triangle. Were you able to follow that, or did I run through that?
No, yeah, that's right.
Okay. Sense. So let's now, do you want us to actually write down the proof, or is that kind of enough to just talk through it? What would be helpful here for you?
Could we write it out, please?
Yes, of course. Okay, so let's start with the S and the R. The first statement are the givens. Angle ADB congruent to angle CDB. AD line segment congruent to DB line segment, and those are given. Okay. All right, so what I would do next is say that angle ADB, comma, angle CDB make up a linear pair. And this is one of those where I'm not sure if you have to actually say this or if you can go right to the next one. That's definition of a linear pair. Because the next one is that the measure of angle ADB plus the measure of angle CDB equals 180. And that's for sure the definition of a linear pair. And I think you probably can go right to that, but I'm not, like, to me, like, what's missing here is like whether they're on a straight line. I mean, I think they are, so you can probably go with that. So now, since you know that ADB is congruent to CDB, you can just substitute that in. You can say, all right, well, it's measure of angle ADB plus measure of angle ADB equals 180. And that's substitution. Okay. All right, so the next step here is to solve. Measure of angle ADB equals 90 degrees. I guess, I don't know, do you ever just say solve, or do you have to actually say like substitution or division property of equality?
Division property.
Okay, because it's really two of these equals 180. You divide. Sorry, I'm missing angles all over the place. If I'm grading this, I'm looking for some step though, that where you say the measure of the angle is 90 degrees. Like that's what you're trying to get to. And that tells you that angle ADB is a right angle. And that's the definition of a right angle. Something like that. Okay, so what we've proven is that ADB is a right angle. Go back to our picture. That means we've got a right angle here, and that's enough to prove that BD is an altitude. This is one of those converse situations. Like if it were an altitude, you could say that it meets at 90-degree angle, but since it's since we proved that it is, you just write the converse of definition of altitude.
Mm. Okay.
So are you comfortable with this idea of converse? Because you're gonna see that at least at some point, you know, whether it's converse of this thing or something else. You know, it's like if it's an altitude, then a bunch of things that we just said are true, that it's a right angle and that's 90 degrees. But if you're going the other direction, then it's always the converse for that.
Right. I got it.
Okay, fantastic. Okay, so we won down. Yay. I don't enjoy proofs. I mean, you know, these aren't like real thrilling, but I hope this helps. I really hope that you've adapted kind of a way of thinking through these that where you can do them on your own for the test.
Thank you.
Where should we go from here?
The next one is number 6. It's like a rhombus, I guess.
Is it
Like
given
a kite
triangle?
shape.
Is it given triangle ABC as isosceles?
Yes.
Okay, got it. There we go. All right. All right, given, okay, triangle ABC is isosceles. There's ABC with base AC. That's really important. What that means is that AB and BC are congruent. It also means that the base angles are congruent like that. Not sure if that helps, but that's what we're doing. Okay. So the conclusion here, the thing that we're trying to show is that BD is perpendicular to AC. All right. So kind of the same as the last one. We need to prove that the angle is 90 degrees. Okay. BD is perpendicular to AC. All right. The other thing that we can do is if we can prove that AE equals EC, I believe that's enough to prove that it's a bisector. But is that enough to prove that's the perpendicular bisector? That's I guess I'm sort of asking that rhetorically, but I'll take a response if you've got it. I don't think that's enough. Bisector proves perpendicular bisector. Yeah, okay. So if you can prove that AE equals EC, that that is enough to prove that this is a perpendicular because it's a bisector. So you can prove that it's the only possibility is it's a perpendicular bisector. Does that sound reasonable?
Yes.
Maybe. Okay. All right. So there's a reason they give you angle 1 congruent to angle 2. So that if you add up these angles, you get a congruent angle. I'm trying to see what triangles you can prove are congruent, and I'm not seeing anything that stands out. I mean, obviously it'd be nice to prove that the upper triangle is congruent to the bottom triangle, or, you know, I'll take the whole triangle congruent to the whole triangle.
Can you do reflexive property with BD?
Yes, absolutely. And actually, we're going to use that to probably prove the whole triangles are congruent. But what I missed here, since angle 1 is congruent to angle 2, that also means that AD is congruent to CD.
Okay.
So what that allows you to do is prove that. Okay, so there's kind of a lot here. Took a deep breath here. So what that allows you to do is prove that the big triangles are congruent.
Mhm.
And that's side, angle, side. And what that allows you to do through CP/CTC is you're going to prove that the little angle is congruent. So
Mhm.
why do you want that? Let me grab the picture one more time to show that. Let me grab those photos. Sorry, just grabbing a snip here. So what that allows you to prove is that if this angle down here is congruent and you already have the side and then the angle and the angle, you can then prove that the other triangles are congruent. Like this. And that means that these sides will end up being congruent. Give me just a moment, please. Is that, I don't know, did that follow all those steps? There's kind of a lot there.
Yes, it made sense.
Okay, so we now have the path. A lot there. So we'll start with all the givens. So statement, we got triangle ABC, isosceles. We got angle 1 congruent to angle 2, and that's the given. So the first thing we will prove is that these upper triangles are congruent. So we're going to first say that AD is congruent to CD, or AB is congruent to AC. I guess the order doesn't matter. Let's do AB congruent to BC.
Okay.
To AB congruent to BC, and that's from the definition of isosceles triangle. Similarly, AD is congruent to DC. So that's this other triangle over here, other side here of the triangle. That's from the fact that the angles are the same. So base angles mean that it's an isosceles triangle. I don't know if you have to say that. I would say like same sides, same angles. Do you know if you're allowed to do that, or do you actually just say that it's an isosceles triangle? Like, do you need to say that ACD is an isosceles triangle because angle 1 equals angle 2?
Just isosceles triangle.
Okay. So somehow we've done that. We're getting really close here. So the only thing we're missing is the angle between this big angle A and this big angle C. So you have to, that's where I would say, okay, BAE plus DAE, those angle measures add together to get the whole angle. And then these angle measures down here, the little one plus little one, they add together. And then you can prove that the whole angles are equal to each other through some type of substitution. But that's what we're going to do next. Is that okay?
Yes.
So the letters here, they kind of matter a lot. Try and do this correct. So the measure of angle BAE plus the measure of angle DAE equals the measure of angle BAD. That's like angle addition property or something like that. Something about adding the angles together. And then in the same step, we can say the measure of angle BCE plus the measure of angle DCE equals the measure of angle BCD. And that's the same reason. That's the one on the bottom there. So what you're allowed to do is switch the ones, like, you know, that from your picture here, you know that this angle equals this angle and this angle equals this angle. So you basically just swap them into the other equation.
Right.
So you have the so you just flip them. So it's the measure of angle BCE plus the measure of angle DCF equals measure of angle BAD. And then switching the bottom for the top, again, measure of angle BAE plus the measure of angle DAE equals the measure of angle BAD. BCD. And that's just substitution. You're substituting in those equal angles. And that's enough to prove now that the measure of angle BAD equals the measure of angle BCD. And that's almost always a transitive property when you're saying, like, since this equals this and this equals this, therefore those must equal each other. You're essentially setting the like this equal to this, and then there are these two angles equal to the BAD, or this one equal to the other one. It's assumed by transitive property that works.
Okay.
Sorry, we're not being more formal, but I mean, we've got a lot of problems to go through, but that's the idea. So that allows you to say that triangle BAD is congruent to triangle BCD through the side angle side. And that's everything we did in the upper picture. That's the postulate that gets the angles congruent.
Right. Okay.
All right. So now that we've proven that the triangles are congruent, that's where we needed to say that this little angle here, BAE, is congruent to angle CAE, or actually, I mean, you're probably supposed to go the whole way, but I think we can get away with using the 3 letters for that. But that's the CP CTC. Corresponding parts of congruent triangles are congruent. So that means that angle ABE is congruent to angle CBE. We're almost done. This proof is basically done from here. Once you have that angle is congruent, you already know that the sides are congruent. You already had the angles congruent from earlier, so you just go angle, side, angle to prove that the triangles are congruent. The order of the letters does matter. Triangle BAE congruent to triangle BCE. And that was angle, side, angle. That allows you to say that AE is congruent to EC. That was the whole thing we were trying to get to. Because if those are congruent, go back to the picture, if AE is congruent to EC, if those are congruent, that means that BE is a perpendicular bisector. We're so happy. And that's what we're looking for. BD perpendicular to AC. And that's again, like, because we've stated all the properties of what a perpendicular bisector is, you go converse of perpendicular bisector.
Okay.
You take a deep breath. Yeah. And these are brutal. I mean, these are not for enjoyment, as to say, as your front of your book says.
No.
Really aren't. Okay, you can see how quickly we go through these, which isn't very quick, but I mean, we definitely do a couple more. We're not going to get through all of these, but you tell me where we should go to next.
I think I can do 14 and 15 on my own.
Okay,
Can we do 21?
sure. So the challenge with this problem is there's no picture. It's rare for proofs and they don't give you a picture. I would not expect this on your test, but I'm not giving it. I would just say that most problems we've done have had a picture, which means you're gonna have to draw a picture. Okay, if the bisector, so go ahead. Sorry, go ahead.
Sorry, I was just gonna say for the final, my teacher said it was gonna be it's gonna be like a word bank of like like reasons for proofs, and then you have to like fill it in.
So you're grabbing like the known steps, and just putting them into your,
Yes.
okay. Well, that's good. A lot of the online homeworks are that way now. If you take a class like that upcoming, you'll see that. So, all right, if the bisector of an angle whose vertex lies on a circle passes through the center of the circle, then it is the perpendicular bisector of the segment joining the points where the sides of the angle intersect the circle. All right, so there's a lot here. Let me do a quick search on this to make sure I actually get the picture right. So if I mess this up, the whole rest of the problem is wrong. I know you don't have that luxury on the exam, but we got to get this right.
Yeah.
Whose vertex lies on a circle, passes through center. All right, well, I'm not finding what I want here. So here we've got a circle. And a vertex angle lies on the circle. But the vertex, I'm sorry, whose vertex lies, it passes through the bisector of an angle. So the bisector passes through there. So we'll just go, there's an angle and there's an angle like that. So these are congruent. That's the first part. If the bisector of an angle whose vertex lies on a circle passes through the center of the circle. Is that part okay? Do you agree with this?
Mm-hmm.
Then it is the perpendicular bisector of the segment joining the points where the sides of the angle intersect the circle. So what they're saying here is that this is a perpendicular bisector. Like you're supposed to prove that those are congruent. You're supposed to prove the triangles are congruent. So I don't know if that's clear or not. Let's see here. We're going to prove, let's label here A, B, C, and then M. We're trying to prove the triangle ABM is the same as ACM.
Mhm.
Passes through the center of the circle, then it is the perpendicular bisector of the segment joining the points where the sides of the angle intersect. Perpendicular bisector. All right, so wow, a lot here. If we could prove those triangles are congruent, we'd be in great shape. I don't think we can do that though. So how are we going to do this? How are we going to do this? So often you have to draw another line like this.
Mhm.
And what that allows you to do is prove that, maybe prove that these triangles are congruent. Call that O for a moment. So we can do that a little bit. We got that's a radius, that's a radius, that's a radius. So what we can do is actually prove that because these are two radii, that this is a isosceles triangle, which means that you can prove that the angle over here is also the same as the angle over here, and similarly get that. So that gets those triangles congruent,
Okay.
which gives you that AB is congruent to AC.
Okay.
Now the reason that's so important, I got to redraw it here. Let me actually just slide this all to the left. The reason that's important is that if we've proven that AB is congruent to AC, and we know that these angles in here are congruent, then we can prove that the triangles are congruent by using reflexive property and get these triangles right here congruent. If they're congruent, that means that through CP, CTC, that BC, BM is congruent to MC, and then we have it.
Okay.
So the thing that I don't think you would know to do is this stuff over here on the left. Maybe you've seen that or could remember that. It's always okay that you always generally want to draw more radii. Is that okay?
Yes.
You follow it? All right. So again, do you want us to work through this statement reason, or just is that enough to talk about it?
That's enough. I got it.
Okay. So if you based on what I've seen for the last two problems, you're going to get one where you have to prove that the triangles are congruent like that.
Right. Okay.
All right, so where should we go from here? What's another question for us to look at?
Can we do 15 on the 15?
15, yes. 15, 15, 15. All right. This median, given KR is a median, is that right?
Yes.
So whenever I see a drawing like this with a lot of lines, I tend to think that I'm going to have to separate out something and redraw just the parts of it that I care about. There's so much here. I assume sometimes you see it. Sorry for the wrong color. So like I see that there's a triangle JKO like that. And then probably, actually need to move this over. There's kind of that one other one that's overlapping there. Like I see KPO like that. That's the kind of stuff you're looking for generally when you're doing problems like this. I don't know if it applies to this problem, but that's the kind of separation that you have to be able to do these. So let me start working on the actual ones that's given. So how about median? What does that mean if KR is a median to JO?
It,
What does that word median mean? If you know.
is that it bisects them?
It's a bisector, but not a perpendicular bisector. So something like that would be good.
Okay.
RP is congruent to KM. There we go. And then RM, wait, RM, wait, I mislabeled this. RP is congruent to KM. RM is congruent to KM. Okay. So that's kind of, I mean, this is written kind of oddly, but let me just put this down here. It's like if RP is congruent to KM and RM is congruent to KM, hopefully you see that they overlap and that RP is congruent to RM. Like that's one of the things we're going to use
Right. Okay.
on there. So basically all of these segments are congruent. So we're trying to prove that JMOP is a, I guess that's parallelogram. I think that's what that's referring to. So we need to prove that opposite sides are congruent. We'd like to say that JP is congruent to MO and JM is congruent to PO. And we can probably do that through this angle stuff. That or through triangles again. Like we're trying to prove that, draw it up here, that it'd be nice to prove that this triangle up here is congruent to this triangle on the bottom, because that will get you the sides.
Okay.
And then similarly, let me grab another snip of this. Similarly, if we could prove that the left triangle is the same as the right triangle, so that this one here is the same as this one here, that'll get you that the other sides are congruent, the JM congruent to PO, and then you've got it.
Right.
So
Okay.
so like our path is kind of clear now. We know that we need to prove that the triangles are congruent, and we're going to do that now. So let's look at the these blue triangles here. So notice you've already got side and a side, kind of. You can prove that MR is congruent to KM. So really this is two lines here. So that means you've got side and a side, side and side. So you can prove that this angle up here, this angle right here, is congruent to the one below it through vertical angles. So if they're congruent, that means that you've got enough to prove the triangle. You can prove side, angle, side, side, angle, side. Do you see that?
Yes.
Okay, so once they're congruent, that means that JP is congruent to MO.
Okay.
And so down here in the second triangle, we got to just draw some more redundant information. Those are congruent, these are congruent, and then you can say that the vertical angles are again congruent. So you again use side, angle, side to prove that they're congruent. Once the triangles are proved congruent, you can say that this other side over here is the same as this other side over here through CP, CTC. And that is enough. So for a parallelogram, I know we haven't talked about that much. So for a parallelogram, there's a lot of ways you can prove that it's a parallelogram, but one is to prove that opposite sides are congruent. It has two pairs of opposite sides that are congruent.
Okay.
So if you've shown that, then it's a parallelogram by the converse again.
Right. Okay.
Excuse me. And that's how I see this problem playing out here. It's probably a 10-step proof. I mean, it's both triangles get congruent. Got that. CP/CTC to get the sides that you want. There's a little bit in the beginning to actually prove that RP equals MR, but you get that from kind of this, RP equals KM and KM equals RM, therefore RP equals RM. There's a transitive property in there. If A equals B and B equals C, then A equals C. That's how you get this piece for that.
Okay.
Any follow-up to that one or anything?
No, thank you.
Okay. All right, so that takes care of 15. What
Next, can we do 21?
Sure. The prove if the bisector of an exterior angle formed by like that one.
Yes.
All right, so it says prove if the bisector of an exterior angle. So we've got to draw a triangle here. So we extend one of the sides. So I guess I'll extend this side. And the bisector of this is going up this direction. So that means that this angle is congruent to this angle. If the bisector of an exterior angle formed by extending one of the sides of a triangle is parallel to the side of the triangle. So that's saying now that these are parallel. The triangle is isosceles. Okay. There's a lot there, like just to even draw it. So just take enough time.
Okay.
For that. So keep that in mind. I mean, if you can't get the picture, you're stuck. I would even ask the instructor if is this the right picture. I don't know if they'll answer that, but that's always a good strategy so that you don't work on something that's wrong. All right, so to prove isosceles, you either need to prove two angles are the same or two sides are the same. And I'm guessing we're going to do angles since this is mostly angle stuff here. Now, if I were to come off to the side here and kind of redraw this slightly differently, let me do it over here in blue. So if you have two parallel lines and it's cut by a transversal, this is sometimes a good strategy. This alternate interior angle is congruent. How does that apply to your picture here on the left?
Could you repeat the question? Sorry.
Sure. So what I'm saying is trying to show you on the right here, if you have two parallel lines on the right here, they're drawn so that they're oriented kind of the same as these here. If alternate interior angles are congruent, how does that help you over here in this triangle? Like what is the mapping, if you will, to the one on the left?
Then the exterior angles are congruent too.
So what I'm looking for now, so I'm trying to show you that this angle that I've drawn in blue is the same as this angle here. Those are the kind of the mapping to this.
Okay, right. Okay.
All right. trying to see what else we can do. If you draw so this is one of those techniques where you end up drawing kind of you're either adding or subtracting lines. So if we look at this transversal right here, and this angle, which corresponds to this one right here, do you see that it is also this angle right there, which corresponds to this one here? So that's what I mean by adding or subtracting lines. You may have to extend a line a little bit to get what you want. So what does that tell you about this triangle here, and specifically these two angles? What do you know about them?
They're congruent.
They're congruent. If you have two congruent angles in a triangle, that means it's isosceles.
Right.
Do you want me to go through that again, or is there something there that we can cover again to help?
It's okay. I think I got it.
This one's all about two parallel lines and a transversal. So this one down here on the bottom is corresponding angles are congruent. Can't forget that. And then the one on the right here is alternate interior.
Okay.
Okay. Is there another problem we can try to start? I mean, I don't know what we'll have time for, but happy to talk through as much from another one as possible here.
Can we do number 30?
30. Okay. All right, find three possible values of the perimeter of kite, K-I-T-E. So I think what they're saying is that it's either that EK is equal to ET or that I'm a snip. I got to grab another snip because they don't tell you like which sides are congruent, or that y squared is equal to 2y plus 3. Because you don't know, like the kite, when it's, I don't know, more well formed, then you know that, oh, this is congruent to this and these are congruent to this, or you don't know if it's this other direction where these are congruent and these are congruent. So that's what it means by that. So you set y squared equal to 5y plus 6.
Right.
And you solve that by subtracting everything to one side. So you get y squared minus 5y minus 6 equals 0. And then you get y minus 6, y plus 1 equals 0. And then similarly on the bottom, you get y squared equal to 2y plus 3. So you have y squared minus 2y minus 3 equals 0. Y minus 3, y plus 1, y equals 3, y equals minus 1. So once you get those y values, and you can see there's overlap, your y is either 6, 3, or minus 1. You plug those back in. Now to find that missing side, which I'm sure you're wondering about, if these are equal, then this one on the top here is 2y plus 3. If these on the bottom are equal, then this is 5y plus 6. And you find your perimeter by putting those y values back in for that for those
Okay.
values. And that gives you, 3 parameters for each of those numbers.
Okay.
So for the proofs, just some guidance. You maybe already heard this, but make sure you always write down your givens. You always can write down at least your last step. You can always sort of like put things into the proof to like get as close as you can. I mean, don't leave them blank. Put as much as you can. Even if you can't prove something, just say it's true so that you can move through the proof. Like the goal is obviously to get them right, but get as much down as you can. Don't say, oh, well, I couldn't get this step, so I didn't get anything else down. And what a lot of students do is they make up for the proofs on the next part of the test if they don't do well on there. But hopefully some of these ideas that we talked about today will help you with the proofs.
Okay. Thank you. Yes.
Yeah. So good luck. If I don't know if we're going to schedule for next week. I'll talk to mom, figure that out. But I think you'll do great. And thanks for letting me help you these last few weeks. I look forward to helping you next year if I don't see you or hear from you until then.
Okay. Thank you.
You're welcome. Bye now.
Bye.